Yeah, just एक बार सब लोग एक बार 28 सुन लो, and whoever asked this, no, when you got it, just tell me कि okay you got it. So 28 quickly, like the first is like find the force on the cone if it's absorbing, fully absorbing. Fully absorbing का एक shortcut है, force is I into projected area by C. तो cone का अगर projected area लोगे perpendicular to the incoming light, you will see a circles. cone को light के direction से देखो, सामने से देखो, circle दिखेगा, right? So circle दिखेगा, इसके लिए the projected area in that plane is pi r square. So I pi r square by C is the force on an absorbing cone. The force on the reflecting cone, this one is easy. Reflecting cone थोड़ा सोचना पड़ेगा. तो reflecting cone के लिए first and foremost, what we'll have to see is as light comes and strikes it, theta is not the angle of incidence. Theta ये जो cone का half angle है, there is actually the angle light makes with the plane. Okay, that's not the angle the light, incoming light, incident light makes with the normal. So the angle it makes the normal is 90 minus theta. जो convenience के लिए मैंने उसको एक छोटा नाम alpha दे दिया, but that angle of incidence this time is actually 90 degrees minus theta. Okay, why does the angle of incidence matter? Because F, the force that is applied is 2I cos square angle of incidence into area by C. That's the formula for reflecting plate. Okay, so therefore that angle of incidence matters. अब क्या है, ये जो force ultimately लग रहा है, वो force normal direction के along लगता है when you have perfectly reflecting plate. ठीक है? Now नॉर्मल डायरेक्शन वाला फोर्स को दो कंपोनेंट में बांट दो, एक होगा ये वाला वर्टिकल कंपोनेंट या कोन का रेडियल कंपोनेंट, इन वे रेडियल डायरेक्शन के लॉन्ग होगा, और दूसरा एक्सियल डायरेक्शन के लॉन्ग होगा, कोन के एक्सिस के लॉन्ग होगा. द रेडियल वन is going to cancel out, so f sin alpha is going to cancel out in pairs because for every point on the cone there is a diametrically opposite point जिसके लिए रेडियल कंपोनेंट ऑपोजिट डायरेक्शन में होगा. जैसे इसमें इस डायग्राम में दिख रहा है डाउनवर्ड एंड अपवर्ड कंपोनेंट्स कट रहा है, पर लेफ्टवर्ड एक्सिस के अलोंग कंपोनेंट्स ऐड हो रहा है एज एक्सपेक्टेड बाय सिमेट्री. द इनकमिंग लाइट बीम हैड नो वर्टिकल कंपोनेंट, is perfectly symmetrical, right? So you would also expect the answer to be perfectly symmetrical. There can't be any bias in the answer. Okay, so you can't have an upward component or a downward component. It should just be towards the left. So what we're going to do is ये सारे force vectors जो है अब जो add करना पड़ेगा, उसके leftward components लेके add करेंगे because we know the others are going to cancel out. Leftward component हो जाएगा f cos alpha. So my net force is basically the summation of f cos alpha over all points on the cone. So technically I have to integrate. The reason I don't really have to perform that integration is because 2I C cos square alpha, these are all constants. Okay, everywhere that cone makes an angle of incidence 90 minus theta. I mean the light makes an angle of incidence 90 minus theta with the cone, everywhere on the cone. So these are all constants. Okay, so even if I was integrating, all these constants would go out and just dA का integration मुझे करना पड़ता है. dA का integration मुझे net total area देगा. So that's how I'm just directly saying 2I total area cos square alpha by C. That is F. This is F आगे की तरफ component. ये net आगे की तरफ force है. We know the other component cancels out on its own. Okay? बस ये actually अपना आंसर है. इसमें मैंने फिर आंसर को area of the cone को pi r L लिखा, and then I just tried to write it in terms of variables already given. L was r by sin theta. Cos alpha is sin theta because alpha is 90 minus theta. इसको simplify करके ये आंसर आ गया. Did you get it? And finally, like if the cone was partially reflecting, partially absorbing, मतलब absorptivity दिया है, then the idea is incoming light का जो intensity है उसका only a fraction is absorbed. So force for that would be, instead of I pi r square by C, it would be A into I pi r square by C. And 1 minus a fraction of the incoming light is reflected. So 1 minus a I is the light which is reflected. So instead of the answer being this, The answer will be 2 I pi r square by c sine square theta into 1 minus a, because 1 minus ai is the amount reflected. Okay, so a times the absorbed force plus 1 minus a times the reflected force. Yes, the third answer aa raha hai. Whoever asked this, did you get it? Did you understand? And it's definitely not an easy question, but did you get the idea conceptually? Let me know. Okay, quickly. Are you not in the meeting? Disconnect ho gaya kya? Anyways, chalo, it's recorded for them. Cool. Let's start Bohr's atomic model. You guys have learned this in atomic structure. This is gonna go by quickly because I don't think there is anything extra that we have to add in physics. है ना? Physics point of view say almost there's nothing new. ये जो तुमने chemistry में सीखा है वही यहाँ पे भी है. So at least this is one of those sections which is exactly the same as whatever you've done in chem. थोड़ा एक background दे देता हूँ. ठीक है? And again, I think right now, I mean, you guys are. Let me just also say this: you guys are attending school, you're attending PACE, you're preparing for your boards, you're preparing for your MT. So there's a lot going on right now. Please don't be under the pressure of having to write. Don't be under the pressure of having to write notes. Okay, you have done well. You have written notes throughout the year. Now you've reached the back end of the course. Let's realize that now it's only solving that helps us actually understand concepts. So I would say even after class, just try to focus more on solving sums than just copying out notes. One of you, Parth, did help me. He gave me an idea of how to convert this into a PDF. For some reason, I think my laptop is not picking up these pages. It's not syncing, but I'll still try to solve that mystery. And I'll try to convert this entire thing into a PDF as soon as possible. Okay? Yeah, enough. Thanks. Yeah. But okay, so I'll try to do that as quickly as possible. But in the meanwhile, just use those PDFs as a reference and focus on solving sums. थोड़ा solve कर लोगे पूरा idea आ जाएगा बोर का. Technically, इसमें जो solving वाला part है is very conceptual. It's one of the easiest topics in all of physics according to me, and according to a lot of people as well. ठीक है, तो जल्दी से एक बार theoretical side देखते हैं. Let's see the background of how this atomic model was developed. Okay. Thomson's model, Leonard's model are not explicitly mentioned in either your advanced or main syllabus. So this page is just more of an FYI. You may need it for chemistry, who knows? But definitely it's good to just know what these guys said. So Thomson's model of the atom was like this. Okay, so this is what did he say? He said the atom is a positively charged sphere and the electrons are embedded in it. Okay, so it's like what some people call as a plum pudding model. Yeah, you can imagine it as a laddu with raisins in it. Yeah, so the atom was like the green laddu, and the electrons inside it are raisins. Now, why did he come up with this model? The reason he came up with this model was because this model explained that thermionic emission mein, on heating this body, only electrons, only negatively charged particles were emitted on heat. Positively charged particles were not emitted. So that's why he came up with this logic. Those electrons are like raisins inside a laddu, and you keep the laddu, the raisins fly out, but the laddu does not fly out. So that was kind of his logic. There was, of course, a big problem with this model. It could not explain Leonard's observations. Okay, same guy Leonard that we heard of in photoelectric effect. Photoelectric wale effect observations, they are in your main syllabus. Okay, but this is a different observation. Leonard का इस context में क्या observation था? He saw कि electrons in a cathode ray. So again, electrons emitted by thermionic emission. Okay, electrons in a cathode ray interestingly pass through the materials of small thicknesses undeflected. So electrons, when they are bombarded on a thin foil, they were found to pass through the foil mainly undeflected. Okay, and his this made him realize that a large part of the atom should actually be empty space, right? If they would have actually hit massive spheres like how Thomson was talking about, then these electrons should have rebounded. Okay, but the fact that electrons could pass through thin foils undeflected in a way implied that um, a large space of the body is actually empty. Okay, a large space of the body should actually be empty. So he was right on track, but when he came up with his model, he messed up a little bit. He said, okay, atoms must have lots of empty space in it. So उसने बोला कि therefore they must be made up of electrons and similarly tiny positively charged particles. तो इसका ultimately ये model ऐसा था. So he did solve the matter कि yes, and a body should have a lot of empty space in it. But where did he mess up? He messed up in the fact कि जो Thomson ने बोला था कि he did, let me finish what he explained. Well, he did explain why electrons in a cathode ray can pass through materials of small thickness undeflected. He did explain that because as you can see in this model, there is a lot of empty space for cathode ray wale electrons to pass through. Okay, but he could not explain why negatively charged particles he emit hota hai on heating and positively charged particles emit hota hi nahi hai. Right? You can't imagine a proton leaving a nucleus and getting emitted on heating a simple body, but electrons get emitted. According to this model, if electrons and positively charged particles were all similarly floating in the body, तो positive वाले particles को भी निकलना चाहिए था. So that was where he messed up, and that's why his model was also wrong. Okay, his model was, just giving you a timeline, was 5 years after Thomson's model. If you guys have any doubts, anything you want to raise, please feel free to ask. These two models were just, in a way, for your information. This one, Rutherford's model, is mentioned in your mains syllabus in physics, and I'm sure it's there in chemistry as well. Okay, so ये थोड़ा important है, but इसमें भी I can't see them ask any numerical question, but it's quite important from a theoretical point of view. It was quite a big breakthrough at that point. He comes, I think, around 8 years after Leonard, and this is what he does. He bombarded a beam of alpha particles on a thin gold foil and studied their deflections. Okay, he bombarded a beam of alpha particles on a thin gold foil and studied their deflections. Most of the alpha particles passed through the gold foil either undeviated or with a small deviation. So in a way similar to what Leonard had done. But I think Rutherford was in a way ready to, his experimental setup was, just to show you a diagram of his experimental setup. ऐसे नीचे ये जो है ना, that was his setup. So he was bombarding alpha particles on a thin gold foil, but he had created a setup where he was prepared to detect where the alpha particles would land. Okay, he was, in a way, he had set up the experiment in such a way he was even ready to detect if the alpha particles should rebound and land somewhere over here. Okay, and this is the experiment he had performed. As a result of his experiment, he saw that, okay, most of the alpha particles pass through the foil either undeviated or with small deviations. However, some, about 1 in 8,000, again, just giving you values, you don't need to remember these, but a very small amount were deflected by very large angles. They either, very, very large angles. Very small amount was deflected by very large angles. So with this, he concluded that since majority pass through undeflected, therefore a majority of the space should be empty. And since only 20 lakhs, is it? 20 lakhs. I'm not sure I follow. Okay. So I mean, based on, okay, 20, okay, you're saying 1 in 20 lakhs for a 180-degree deviation. Fair enough. Great, great. So apparently there was 1 in 8,000 which were deflected by large angles, and 1 in 20 lakhs which were deflected by around 180 degrees is what one student is telling me. So yeah, quite interesting. Key, a very small portion of that foil, therefore ओनली एक छोटा पोर्शन ऑफ फॉइल के साथ ये अल्फा पार्टिकल हेड ऑन कोलिजन कर रहा था, राइट? यस, 1 in 2 million 20 lakh सेम थिंग. तो हेड ऑन कोलिजन कर रहा था. हेड ऑन कोलिजन पे ही वो 180 डिग्रीज वापस लौटेगा. सो यू कैन इमेजिन कि यार हेड ऑन कोलिजन अगर इतने कम अल्फा पार्टिकल्स कर रहे हैं, राइट, दैट मींस कि यू हैव और ऐसा लौट के आ रहा है. अल्फा पार्टिकल इज अ हीलियम न्यूक्लियस, राइट? तो ये helium nucleus का mass is of course like molar mass is 4 grams. So you can imagine कि there is a far more heavier particle inside the gold nucleus, जिसके साथ ये alpha particle बहुत ही rare occasion में head on collision कर रहा है, implying कि a very small part of the atom is made up of a very heavy particle capable of deflecting the alpha particle by large angles. So this is what he realized. And based on the numbers, based on the number of alpha particles that were deflected by large angles, he in a way did the math behind it, and he proposed that the atom is made up of a small positively charged particle called the nucleus, okay, and then a sufficient amount of electrons to maintain neutrality. Sufficient amount of electrons मतलब जितना न्यूक्लियस का चार्ज है उतना ही नेगेटिव चार्ज होना चाहिए, because overall it was neutral. So almost for the same amount of charge, an appropriate amount of electrons to maintain neutrality would rotate around the boundary of the atom in a circular orbit. Okay, and he said that the space between the electrons and the nucleus is empty. Space between the electrons and the nucleus is empty. In fact, he estimated the radius of the nucleus to be of the order of 10 to the power minus 15 meters, based on what he did. And it was, I think, already known at the time that the atom ka size is approximately 1 angstrom, 10 power minus 10 meters. And this is quite good because this is more or less true. Nucleus ka size is more or less of that order. So this was quite close. This also makes the volume of the nucleus. So this makes the radius 1 upon 10 to the power 5 times the radius of the atom. Okay, the radius is 1 lakh times smaller than the atom ka radius. Nucleus ka radius is 1 lakh times smaller than the atom ka radius, and volume to radius ke cube ke proportional hota hai. So this made the volume of the nucleus 10 power minus 15 times smaller than the volume of the atom. Okay, that's what his math proved. And I mean, we in a way now know how atoms in a way are, but you can imagine why this was so shocking, right? We don't perceive solid objects to really have a lot of empty space in it. The solid objects do, right? Every object around us has a lot of empty space in it. I mean, the basic building block जो है an atom, उसमें majority of the mass of the atom lies in a very, 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 very small part of the atom. Okay? And the rest of the mass that जो काफी छोटा होगा in comparison, electrons का mass, they are, you know, floating around the space surrounding the nucleus. So it was quite, I think, revolutionary at the time. Rutherford, nonetheless, just to show you his setup looked like this. You might have definitely seen this diagram before. again, the graph, the values on the graph are not exactly important. Maybe your CBSE board and all requires you to remember certain values. I think perhaps that's why you guys are good with um, values on the go. But the overall gist of this graph is, as you can see, smaller angles, I think a zero deflection, a small deflection, there were a lot of particles. Whereas for large deflections, there were very few particles. So the number of scattered particles based on the angle they were scattered by decreased as you went for, as the scattering angle increased. That's of course the gist of the experiment. And just from a theoretical point of view, you should understand what he observed and what was the conclusion because of what he observed. So the conclusion was there's a lot of empty space, but there is a very, very heavy particle located in a very, very, very small region. And we now know that heavy particle in a small region is our nucleus. Okay. The drawbacks. If you guys have any doubts, please feel free to jump in. You feel you want to add something, you can add things as well. Does the screen absorb? I've not really seen what the screen does. Does the screen absorb electrons? I'll have to, I'm not very sure what is the mechanism by which he's detecting the electrons. Obviously, it should absorb. I mean, I can answer that question. It should absorb, but now, if it reflects, if it does not absorb the electron, फिर electron जाके और किधर भी hit करेगा ना, तो yeah, definitely it's not reflecting the electron. तो उतना तो हो रहा है. It's definitely absorbing the electron. And exactly कैसे somebody saying bright spots are seen when the electron strikes the screen. वैसा कुछ effect हो सकता है बिल्कुल. Yeah, but definitely the electrons were not getting reflected. That would be a redundant experiment. Because जो electron उधर hit कर रहा है, फिर वो इधर भी पहुंच के यहाँ पे भी एक hit record करेगा, वहाँ पे भी hit record करेगा. So definitely, I mean, I'm sure he's smart enough to ensure कि the electrons don't get reflected. वो result से भी समझ में आता है कि they are not getting reflected. Yeah, they're getting absorbed, and there's some way it's being detected. Okay. So I'm being told that the screen is made up of zinc sulfide and chemistry हो जाएगा ये, but probably something happens when an electron is absorbed by zinc sulfide, which, yeah, fluorescence. Okay, fluorescence effect दिखता है. Okay, great. Ionize होता रहेगा, ऐसे कुछ होता रहेगा. Okay, good. All right. So now, what were the problems in your Rutherford's model? So, Rutherford, first of all, his model could not explain the discrete wavelengths observed in hydrogen's emission spectra, right? So we're going to see it in a bit, but I'm taking advantage of the fact that you know what hydrogen's emission spectra is. You know the Lyman series, you know the Balmer series. So Rutherford's model could not explain that in any way, because Rutherford's model had no concept of orbits. Okay, maybe when you heard Rutherford's model, it sounds, hey, you must have thought, hey, this sounds like the atom we know. It actually doesn't. He is right about the nucleus being very small and heavy, but what you may have missed is in his model, the electrons are at the boundary. There's no concept of an orbit. According to him, electrons were at the boundary of the atom, and the nucleus was at the middle of the atom. Electrons were at the boundary, and he justified electrons not getting attracted to the nucleus by the simple Earth satellite model. कि electron घूम रहा है, तो electron का electron पे जो centrifugal force लगेगा, वो nucleus का attractive electrostatic force को counter करेगा, इसलिए electron nucleus की तरफ जाता नहीं है. This was his model. Okay, this was his model, and we know that there are some problems with that, and we'll come to those problems. But the fact is, because he didn't have any phenomena of orbit, different orbits and different energy levels, he just could not explain why we see the hydrogen spectrum. All right. He proposed that the electrons move in a circular orbit, and thus the centrifugal force cancels out the electrostatic attraction towards the nucleus, as I mentioned. But Maxwell's equations, okay, so I think Maxwell came up with his equations a long time before this. I think in the 19th century, between 1800 and 1900, his equations are out. And what his equations basically implied is that I don't know where you guys have reached magnetism, but you probably know that a stationary charge creates an electric field. A stationary charge creates an electric field. A charge moving with constant velocity creates a moving electric field, and thereby it creates a magnetic field. So charge moving with constant velocity creates a uniform magnetic field, but a changing electric field. An accelerating charge ends up creating an electromagnetic wave. Why does that happen? So Maxwell's equation says that when the electric field changes, the magnetic field around it should change. Okay, when the electric field changes, the magnetic field around it should change. And when the magnetic field changes, which is what you learn in EMI, electromagnetic induction, the magnetic field change hota hai, the electric field around it should change. Those are Maxwell's equations. So what happens in an electromagnetic wave is, when a charge accelerates, it's creating, first of all, a moving electric field and a moving magnetic field. And those two, in a way, support each other. Okay? And the changing electric field further creates a magnetic field. The changing magnetic field further creates an electric field. And you have this beautiful harmony, jiske karan an electromagnetic wave propagates. Okay? And this may seem absurd, but trust me, this is something we are actually encountering on a daily basis. We are all using communication systems. We are all using electronic devices which use the internet, or we make phone calls, or I don't know who uses the radio anymore, but right, even if you use the radio, there are signals going from one place to another place. All those signals are in the form of light, specifically low intensity light, that is radio waves. So specifically in the form of radio waves, we have signals being sent. How are those signals sent? How is my voice reaching you? So we'll see a bit of that in the chapter called as communication systems, जो mains के syllabus में है. But basically what happens is, Maxwell's equation say when our phone has a transmitter. Okay, so my voice is being recorded on my phone, or is going to my phone. My phone is then accordingly moving a charged particle inside the transmitter. Based on how it moves the charged particle, a radio wave is created. Okay, a radio wave is created. That radio wave ka frequency carries the message. The radio will not be a pure sine wave. Its frequency will carry the message that my voice is in a way sending out. So it's quite fascinating. That finally ultimately reaches a receiver, and your receiver decodes the message from that radio wave, and then you hear my voice amazingly the way I'm speaking over here. So थोड़ा detour में गया, and it's of course not as easy as I'm putting it. I mean, it's far more complicated than that. But the bottom line is, moving charges emit electromagnetic waves. If they could not do that, our entire communication system, the way we have it, would not have been possible. Ayush, we'll see about that. Okay? So, yeah, but coming back to this, yeah, Rutherford proposed there is only one orbit. Yes, so Rutherford ke hisab se there was, this is a little subtle, you may not be clear about that, but Rutherford proposed that the electrons move on the boundary. इलेक्ट्रॉन सिर्फ यहाँ पे इधर देख लो, या सेकंड पैराग्राफ, second last line, they rotate around the boundary of the atom in a circular orbit. Okay, okay, so इससे क्या आया? हाँ, so Niels Bohr improves on this. Niels Bohr improves on this idea, but let me just wrap this up. So he says ki moving electron, sorry, we know ki moving electrons should emit, accelerating charge should emit electromagnetic waves. Accelerating electrons should emit electromagnetic waves. This was a problem. Okay, this was a problem. So if the electrons were emitting EM waves, kya hota tha? They're emitting waves. Waves have energy. Okay, light has energy. So if it's going to emit light, it's going to lose energy. The electron is going to lose energy, and it should spiral towards the nucleus. It should collapse. That's the biggest problem. It's not a stable model at all. It should collapse. So sometime later, what is it? Right? So that's the biggest problem. This is a side note, like while it is collapsing, moreover, while it's collapsing, the radius of the electron will keep becoming smaller. Accordingly, the wavelength emitted will also change. Okay, depending on the wavelength emitted will depend on the frequency of rotation. The wavelength emitted will change, and therefore, if at all you should see a spectrum while it's collapsing, you should see a continuous spectrum, not discrete spectrum like we know in the, like we have seen in the Lyman Balmer series, etc. So we should see a continuous spectrum. This obviously does not happen. But more than the last point, the basic idea that the electron will spiral towards the nucleus and the atom would collapse is a crazy idea, because then the atom is not stable. Right? What happens after that? So that was one big problem with Rutherford's model, which, okay, somebody is giving me facts. It will fall to the nucleus in less than 10 power minus 8 seconds. Okay, so what he's saying is right. The atom should destabilize really soon. It should collapse really soon. And what do we do after that? Okay, what do we do after that? No one knows. So of course, the Rutherford's model has to be then in that case put aside. So with that, we'll finally enter Bohr's atomic model, which, if you look at the timeline, this is just 2 years after Rutherford's model. Okay, so then there's some credit due over here for the extra insight that he has. His model is not perfect. In fact, we know this model is not right. We're gonna see that based on what we know now from Schrodinger's equations. We know this model is not exactly right. But let's just see what this model is. So he says the electron revolves around the nucleus in circular orbits. Okay, first point, where the centrifugal force still counters the electrostatic attraction towards the nucleus. Well and good. Just like Rutherford's model, ये भी बोल रहा है कि centrifugal force counters the electrostatic attraction towards the nucleus. But second point में थोड़ा फर्क आ रहा है. He's saying the orbit of the electrons around the nucleus can take only special values of radii called as stationary orbits. So he claims that these orbits cannot be of random size. There are multiple orbits, and all these orbits have specific radii, and he'll imply later that they have specific, when an electron orbits in them, the electron has specific energies as well in these orbits. So these orbits are like energy levels, is what he concludes. In these orbits or special radii, he says the electrons do not radiate energy as expected from Maxwell's laws. We'll try to understand why a little bit later, but he definitely does not explain why. But वो एक्चुअली करता क्या है ना, उसको दिखता है कि लाइमन सीरीज, बामर सीरीज में ये सब लाइट निकल रहा है, तो वो सब लाइट, वो वेवलेंथ देख के ही कंक्लूड्स कि these wavelengths must be coming when photons are emitted. And then he makes a very smart, with that he nicely realizes that there must be energy levels in the atom. And when an electron jumps from a higher energy level to a lower energy level, certain wavelengths should be emitted. So based on those wavelengths, he realizes what the energy levels should be. And from those, he manages to get what the radius should be. Okay. Because with the energy, you can get the radius. Even when the moon is orbiting around the earth, if I tell you the energy, you can easily come to know the radius, because energy depends on capital G, the two masses, and the radii. Right? So with the energy, he has probably concluded the radius. He had no explanation to why those specific radii may Maxwell's law in a way follow nahi ho raha hai, ya energy वैसा lose nahi ho raha hai. He had no proper explanation for that. Okay, but he did get those, more or less he did get those precise radii. Okay, so he just says कि अब ये radius में for some reason Maxwell's law is not being emitted. Maybe his guess was कि जो भी ऐसे special radii में जो भी EM waves emit हो रहा है वो तुरंत absorb हो रहा है by the atom. So there is some kind of harmony where whatever the electron is in a way emitting, it's absorbing back. So for some reason, it's not radiating energy, and we'll try to understand this a little later from the wave nature of an electron. So that's point 2. Point 3 is Bohr's quantization rule. So based on the radius he got, फिर उसने वो radius देख के उसने angular momentum निकाला उन orbits का, मतलब electrons जब वो orbit में है तब angular momentum निकाला, वो निकाल के दिखा रहे यार इसका value अच्छा लग रहा है, मतलब this looks nice. So then he came with this theories कि the angular momentum of the electron is an integral multiple of nh by 2 pi. Okay, why should it be this? That's not something he has proved, but he has predicted what the radii should be. Based on the radius, he knows what the velocity should be. We'll see those equations. From that, he gets the angular momentum. Radius का जब तुम formula देखोगे थोड़ा सा गंदा सा है. Velocity का formula गंदा सा है. Momentum का गंदा सा है. Angular momentum का अच्छा सा है. nh by 2 pi. So that sounds like a nice headline, right? So therefore, he framed his entire working under this rule. He stationary orbits में angular momentum of the electron is an integral multiple of nh by 2 pi. H is, yes, H is the Planck's constant. H is your Planck's constant. Okay. Now, the next one is the Einstein-Planck equation. So, in different orbits, the electron has different energies. Okay, I think Einstein came up with this with the photon wala principle, I think in 1905. So this guy has seen that, and he's using that over here. In different orbits, the electron has different energies. Therefore, if an electron jumps from one orbit to another, it either absorbs a photon or emits a photon of energy equal to the difference in energies. Yes, Aditya, yes. Equal to the difference in energies. So the difference in energies, जो energy levels में difference है, उसके हिसाब से इलेक्ट्रॉन या तो ऑब्जॉर्ब, उसके हिसाब से फोटोन या तो वन फोटोन ऑब्जॉर्ब होगा या वन फोटोन एमिट होगा. Sorry, एक सेकंड ना. Is my voice clear? I think I got a call in the middle. I think it's fine now. Okay. एक सेकंड. तो हाँ, this theory was कि एक ही फोटोन एमिट होता है इन ट्रांसिशंस के लिए. It's not multiple photons, and it in a way lines up with what we observe. So I think that just happens for these exchanges, for these jumps, it's always one photon that's absorbed or emitted per electronic jump. So jitna energy difference hai, that corresponds to h nu ya hc by lambda. Okay, that's the energy for photon. And I think one of you is telling me ki h by 2 pi, probably you guys know this better. H by 2 pi को जब तुम with a bar लिखोगे, that's called as reduced mass. Okay, fine. That's called as reduced Planck's constant. That's what you're saying. Okay, fair enough. H by 2 pi apparently is shown by another symbol called as a reduced Planck's constant. Okay, all right. But yeah, coming back to this. So I think the fourth postulate is the most logical one. Fourth postulate is the most logical one. It makes sense. It makes sense. And my guess is that he probably understood this. And with this, he backtracked and found the value of the radius. And then just said, ki ye radius hona chahiye. For some reason, Maxwell's laws are not obeyed. And then even with 0.3, I feel he doesn't directly land on that. But with the radius that he has, and with the velocity expected for that radius, he probably sees like what would be a good headline. So R ka formula ganda hai, V ka formula ganda hai, momentum ka ganda hai. Just so happens angular momentum happens to usme Z वगैरह cancel hota hai. A lot of constants disappear. You're left with NH by 2 pi. So he comes out with this amazing result. Without understanding why, to get a result like this is quite amazing. We'll try to make some sense of why the result is what it is. But these were Bohr's postulates. Now, okay, again, from a theoretical point of view also, those postulates are important. You should have an idea of what his claims were and why he made those claims. I can notice a slight lag in my, I think that's just in my device. Okay, okay, fine, fine. अब ठीक है, ठीक है. It's clear now. Okay, fine. Limitations of Bohr's theory. Okay, what were his limitations? Okay, so this is the first one. His theory takes into account that there's only one electron. Okay, it's Earth Moon system ki tarah wo soch raha hai. So like there's just one electron in it, and it doesn't take into account the fact that there are other electrons as well, and therefore his theory does not work for atoms or ions with more than one electron. And even if you try expanding that, the math does get quite complex. So no problem there. But yes, his theory is limited to one electron atoms. Therefore, whenever you find a question in Bohr's model, ya to you'll find a question for a hydrogen atom. Yeah, if they want to play with the atomic number, because some of these formulas depend on the atomic number, so thoda variation ke liye they'll say, acha, helium plus iron. Yeah, I can't imagine a helium plus iron existing. Helium is supposed to be inert, but you know, helium plus iron, Li2 plus सवाल बनाने के लिए कुछ भी लिख सकते हैं. So these are the kinds of atoms you may see. Okay, monovalent की बात नहीं है. One monovalent, ठीक है. Exactly one electron in the entire atom. ऐसे kind of atoms के लिए his theory in a way works. ठीक है, hydrogen-like species would be, yeah, that would be a nice phrase for it. So hydrogen-like species. Okay, He plus, Li2 plus. इनके लिए this जो भी जब भी सवाल देखोगे, सवाल में ऐसे type of atoms तुम्हें दिखेगा, wherein that just has one electron in it. There can't be two electrons, otherwise you can't really apply Bohr's theory on it. So that's one limitation. Does not work for more than two electrons. Okay. Somebody is telling me that Sommerfield's model is an expansion of Bohr's model. Okay, you guys, those who are interested can look that up. Probably sounds like something you must have learned in chemistry. You can look it up. हो सकता है electronic screening वगैरह थोड़ा, if you take into account, you can make some adjustments. But I think, yeah, Bohr's theory on its own doesn't go beyond one electron, doesn't work for that. The second point is interesting. I saw this in the HCV. So it said ki as technology nowadays has allowed for more precise measurements of wavelengths, slight deviations from Bohr's predictions were observed even in the hydrogen spectra. What was earlier one wavelength was observed to comprise of multiple nearby wavelengths. Matlab, just to explain what that meant, like what people knew as a particular, let's just take for example, what people knew as a particular line in the Lyman series. Okay. On closer examination now with our modern technology, people realize that that's not one line, but there are, around like seven different lines very, very close to each other. The minute you take that into account, then Bohr's theory falls apart, because there's no way to Bohr's theory nicely explains why there could be one line for a particular jump, but why could there be 7 different lines very close to each other for that kind of jump is not something which his theory in a way could explain. So that's one slight problem with it. I mean, that's one slight problem that we see now. Okay. So it doesn't work well for hydrogen as well. And I'll talk about why his atomic model isn't exactly correct. By Heisenberg's uncertainty principle, okay, which comes in a little later, and the quantum mechanics model of an s orbital that we now know, right? You've heard of Schrodinger's equations, and you probably now know what an s orbital looks like. So it's not like the orbit of the moon around the earth. It's not a circular orbit. Okay, in fact, it's spherical in shape. Moreover, it's not कि एक पतला सा thin sphere है जिसमें electron move करेगा. Rather, it's an entire region. It's a cloud-like region जहाँ पे there is a probability distribution of finding the electron at a particular place. Yes, so based on the radial distance, okay, based on the distance from the atom, the probability distribution looks something like this. All right, so beach mein there is a large probability of finding the electron. So Bohr's orbits probably correspond to those peaks. So yes, indeed, there is a particular distance where there is the greatest probability of finding an electron. But again, that's just the greatest probability, and that's not 100% probability. Electrons do not move at a fixed distance from the nucleus. They do not move at a fixed distance from the nucleus. Okay. Reason being, so how do we realize कि how does Heisenberg's uncertainty principle tell us कि यार electron एक circular path में जा नहीं सकता है, fixed circular path में? Because Heisenberg's uncertainty principle tells. Sorry again, random people are calling in case it block करे. So his principle says based on the wave nature of an electron, you can say कि electrons linear momentum and its where was I? Its position and its momentum cannot be narrowed down beyond a certain value. Right? You can't precisely know both its momentum and its position. If you are going to treat the electron as a particle moving at a specific, moving along a specific radius, you're pinpointing it to a specific position. Moreover, if it's going to be in that particular orbit, then its velocity also becomes specific. So in a way, you're pinpointing both its velocity, that is its momentum, and its position to be a particular value in your model, which is a violation of Heisenberg's uncertainty principle. Okay, so these are complex things which we can only understand when we leave the notion of the electron being a particle only and embrace the notion of it being something different, being a wave at the same time. All right, so coming back to this, based on Heisenberg's principle, we now know कि electron actual में एक circular orbit of precise radii में जाता नहीं है. What were precise radii in Bohr's atomic model become most probable radii in the quantum mechanics model. Based on the probability distribution, electrons could be found in between these stationary orbits as well. This is probably why on closer examination, we don't see now a single line for a particular energy jump, but we see several lines close to that. Okay, so it's quite possible that, in fact, the electron is not going to be at a fixed distance from the nucleus. It could be found a little inside the orbit, a little outside the orbit as well, okay, based on the probability distribution. It will be quite close to the orbit, which is why he was experimentally able to justify those lines being there. Okay, and the value of the radii he got uh, can be justified by quantum mechanics as well. We're going to see that can be justified by quantum mechanics as well. But um, there can be slight deviations because the electron exactly its circular orbit में जाएगा नहीं. So as you see, visualize the S cloud of an electron. That's great. The S orbital कैसा दिखता है? That's great. That's a good way to visualize the electron. But also bear in mind कि that's again a static model. Electron definitely move कर रहा होगा. Okay, so that the S cloud is like a heat map. Electron किधर किधर हो सकता है, but it's definitely moving around the nucleus as well, and that's another reason why it does not collapse to the nucleus. So there is that sense of movement, and it does tend to pick certain distances where it does not radiate energy as expected by Maxwell. So it does have that nature, but it moves not in a circular orbit, moves in a more like a spherical kind of orbit. Well, the plane of the circle is not fixed, so it could change the plane in which it is orbiting. ठीक है, थोड़ा coming back to where we were. Point 4, Bohr couldn't explain why the electron doesn't radiate energy in those orbits. He didn't explain that. Where the angular momentum is an integral multiple of h by 2 pi, he just assumed this was possible. So why don't we, I mean, if we know now that Bohr is wrong, why isn't it abandoned? To give him credit, Bohr still explained the hydrogen spectra reasonably well. Reasonably well. Okay? He could not explain these smaller lines, but still, I mean, more or less, his model was not that off. And he provided a simple model of circular orbits that non-physicists and beginners could understand. All right. So, in fact, if kids in school, the reason why in school we again teach everyone, you might have had your teachers tell you कि यार जो school में तुमने सिखाया वो पूरा गलत है, electrons as a circular orbit में घूमते नहीं है. You must have heard chemistry teachers say that. That's fair enough. That's true. School did teach us a bunch of wrong things, but I mean, what do? You can't teach kids Schrodinger's equations and tell them about probability distribution and electron clouds and all of that. They don't know, they don't care, they don't even know if they like science. You can't give them a reason to hate it all the more, right? So I think the Bohr's model in its place is good enough to give at least to introduce or help people who are not interested in physics at least have some idea of what an atom looks like and what an electron could be doing inside the atom. I don't deny that the electron is moving around the atom. I don't deny that centrifugal force and electrostatic attraction force are at play with each other. थोड़ा अंदर जाएगा, थोड़ा बाहर जाएगा. ठीक है? The orbit may not be perfectly circular, may be elliptical, may be not confined to a specific plane. Okay? And this is all not taking into account the actual wave nature of the electron. But still, Bohr's model is good enough to at least teach people who are not that interested in physics. Just at least give them an idea of what an atom is. All right, so that's why it's not been completely discredited. Moreover, we shall even see how de Broglie explains point 4 with the wave nature of electrons. All right, so it's quite interesting that this result, integral multiple of h by 2 pi, can actually be explained and justified with the wave nature of electrons. So if nobody has anything to add, Feel free to ask doubts. Feel free to add. Even my knowledge in this area is limited, but of course, learning some things from you guys as well. So De Broglie's explanation of Bohr's quantization rule. Let me just see when this came in. So this is 1927, around the time of Heisenberg's uncertainty principle, and several years after Bohr's atomic model. All right, so this is how De Broglie explains it. Okay, so he says that an electron is a wave, and okay, we know that electron is a wave, cannot be isolated. It cannot be isolated to a single point in the orbit, because that's a violation of the uncertainty principle. The electron would rather appear to be like a standing wave in the orbit. All right, so even the model of just visualizing the electron like a particular particle at a particular point of time moving through the orbit, even that model is a violation of Heisenberg's uncertainty principle. Yes, we know circular orbit itself justified nahi hai. Actual orbit spherical hoga और थोड़ा अंदर बाहर जाना allowed होगा. But even if we now just narrow it down to a circular orbit, usme be trying to explain things by looking at the electron as a ball moving in this orbit, like a moon moving around the earth, that is wrong. Because the minute you do that, you're considering the electron to have a specific position and a specific velocity. Okay, that's a violation of Heisenberg's uncertainty principle. In fact, the electron's position in this orbit cannot be known. In fact, more or less, if you're going to pinpoint the orbit, uska velocity काफी हद तक fix हो जाता है, so its position cannot be well known. So you'll have to visualize the electron as a wave in this orbit. If you're saying the electron is moving in this orbit, if it's saying its velocity is momentum is more or less narrowed down to this range, then the electron's position cannot be determined inside that orbit. So inside this orbit, the electron would look more or less like a wave. Okay. So now imagine this. So given that embracing the wave nature of an electron, if the electron is like a standing wave in this orbit, why, if you look at standing waves on a string, he said when you notice standing waves on a string, with both ends fixed, these standing waves occur not for all wavelengths. In fact, there are certain modes of oscillation. Standing waves occur only for those wavelengths which ensure that there is a node at the end. Yes, Aditya, yes. So standing waves occur only for those wavelengths which ensure that there is a node at the end. Thus, we get discrete modes of oscillation. All other modes die out, right? So, like for instance, if you look at a string, jiska length is L, we immediately know that the kind of wavelengths the string can have can be 2L, first mode, or it can be L itself, second mode, or it can be 2L by 3 and so on and so forth, right? So 2L by N, yehi wavelengths allowed hai, because yehi modes of oscillation mein that end point behaves as a node. Why isn't any other value of L possible, right? Why can't lambda be 5L? Lambda cannot be 5L because यहाँ पे फिर node नहीं आएगा, right? So there are these kind of, so even in waves on a string, the other modes of oscillation automatically die out. Other modes of oscillation automatically die out. In fact, you can do this experiment with a guitar string. Guitar string mein wherever you plug, so when you plug the guitar string, several modes of oscillation are set up. ये नहीं कि सिर्फ एक मोड ऑसिलेट होता है, मतलब सिर्फ फंडामेंटल मोड में ऑसिलेट होता है, क्योंकि सिर्फ फंडामेंटल मोड का जो आवाज होता है, that's like a pure sine wave. If you remember, I made one video in Beats using sine waves, and that sounds very boring. Just sine wave by itself, it's a very boring sound. It does not have any texture. The reasons instruments and the human voice and all sound nice, because our voice is not just one sine wave. It's a combination, a superposition of the fundamental and many overtones. और अलग अलग instruments में overtones का amplitude अलग अलग होता है. That's why a piano sounds different, a violin sounds different, the guitar sounds different. When you're going to pluck a guitar, based on where you plug the guitar, आवाज थोड़ा थोड़ा change होता है, but it still sounds like a guitar. So in reality, the modes of oscillation aren't severely getting affected based on where you plug the guitar. Even if I pluck it at a point which can never be a node, let's say I pluck it at a distance L by pi from one end, still L by pi can actually never be a node, right? Because you can't have integral multiples of it finishing over there. So even if you pluck it at some weird point जो कभी node हो नहीं सकता है, वो जो oscillation लाने की कोशिश कर रहा है, that oscillation would die out and the fundamental and overtones would remain, right? So what De Broglie is saying is, the way in a standing wave, wrong modes of oscillation die out, but certain other modes of oscillation remain. Similarly, when the electron is visualized as a standing wave in this orbit, in this circular orbit, when the electron is visualized as a standing wave in the circular orbit, okay, this is what he says. Electrons can only revolve in those orbits which allow a standing wave to be set up in it as given by the De Broglie wavelength. मतलब क्या बोल रहा है वो? The circumference of the orbit must be an integral multiple of the De Broglie wavelength. Circumference of the orbit has to be an integral multiple of the De Broglie wavelength. Okay. So Yash, I'll try to answer your question. So basically, but just to give you an idea of what this diagram is, so he's saying ki, if the electron looks like a standing wave, as you move around the orbit. Now we know in reality it's not a circular orbit, but at any point of time, even as the electron is revolving around the atom, its distance is not exactly a particular value of r from the nucleus, but it's still most probably something close to that value of r. Okay, so that particular distance, the circumference of the path it could follow, should be a pure multiple, should be a multiple of the wavelength as given by De Broglie's equation. एक बार let's see what this means, and I'll try to explain that a little bit further. But just see how this purely brings out Bohr's quantization rule. So ये electron जिस path के along अब move कर रहा है, फिलहाल that path length is 2 pi r. For us to set up a standing wave in this circular orbit of length 2 pi r, है ना? तो standing wave अगर दिखना चाहिए, standing wave का length, right? Since this is a closed loop, तो standing wave का length हो जाएगा n times the wavelength. There should be n repetitions of the wavelength. So some number, some integral multiple of the wavelength is the circumference. The 2 pi r is n times wavelength. The De Broglie wavelength is h by momentum, h by mv. So 2 pi r is nh by mv. Bring mv to the left hand side, bring 2 pi to the right hand side, you get mvr as nh by 2 pi. So this Bohr's quantization rule, which seemed correct, I mean the math added up. Okay, he didn't know why it worked, but the math added up. This rule can be explained. In fact, this rule and seeing how it works out with De Broglie makes us understand that an electron in this confined space looks like a standing wave. Later, when you learn quantum mechanics in your first year of engineering, you'll understand that if an electron is in a box, it's not a particle inside the box. It's like a standing wave set up inside the box with several modes of oscillation. So that's how the wave nature of the electron in a way behaves. So यहाँ पे 2 pi r has to be n times the De Broglie wavelength. Why again? If 2 pi r is not n times the De Broglie wavelength, for instance, like if you're wondering why can't 2 pi r be 2.5 times De Broglie wavelength, तो ये देखो, ये एक repetition हो गया, ये दूसरा रेपिटेशन हो गया और ये अब आधा रेपिटेशन हो गया. So you can imagine कि if I need to now form a circular loop with this. So I can't loop this around because that's not going to look like a legitimate standing wave. एक repetition, दूसरा repetition और आधा repetition, right? So this does not work out. This mode of oscillation is not going to work. On the other hand, if you consider this, consider 2 pi r being 3 lambda. So now you can see how this can be closed around into a complete loop. Okay? So I don't think it's easy to draw this. One loop, ये नीचे गया 2 loops, ऊपर जाके वापस नीचे गया 3 loops, right? And इसका मतलब ये इसका wave nature is not, it's not a particle type wave nature कि वो ऊपर नीचे जा रहा है. It's not a position based wave nature. It's something totally different. But that's kind of the idea. This was Bohr's explanation, and this is the only way we could explain why these specific orbits work. So the only way to understand is just like in a string, there are certain modes of oscillation. Value of n is not 3. Value of n, so n can be any integer. When n is 1, it's the first orbit. When n is 2, is the second orbit. When n is 3, is the third orbit. When n is 4, is the fourth orbit. So it can be any integer. Ha. So even like when you the whole idea is like even if you're trying to force oscillation in any spring, in any guitar string, you're trying to force oscillations in any pendulum, you'll automatically see that it does not take up your oscillations. You can't easily, even when you try to push someone on a swing, you can't just push it according to your own frequency. It has a natural frequency and you have to line up with that. You have to line up with that frequency. What happens if, you're trying to push someone on a swing and your frequency does not match with that person? वो वापस तुम्हारे तरफ लौटने के बीच में you push him again. फिर वापस लौटने के बीच में push him again. There are severe energy losses in those kind of cases. But when you wait for this guy to come back to the top and you push him, when the frequency of your pushing and the frequency of the swing is in line, that's when energy is conserved, and that's the idea of resonance. It's a very simple, cheap way of explaining something जो complex differential equation से आता है, right? Now the same idea with waves. You don't have just like unlike a pendulum जिसका एक ही mode में resonance हो सकता है, exactly frequency match होना चाहिए. But waves में you have I could be wrong in that as well, but waves में you have several ways in which you can have resonance, right? When the fundamental can remain, the overtone can remain, right? So whenever whatever you're trying to induce is related to is either the fundamental or one of the overtone frequencies, energy is in a way conserved. But if you try to force a guitar string to oscillate in a mode it's not supposed to oscillate in, that energy is going to die out. And we can understand what forces could be in play in a guitar string. Maybe that particular mode of oscillation is trying to pull very hard at the node, right? It's going to try to pull very hard at the fixed end, and it's going to try to say become like an anti-node. The fixed end is not going to respond to that, right? So in that process, certain portions of the string may get stretched unnecessarily, and it may lose energy in that kind of manner. Maybe it's not very easy to realize what is happening exactly in this, like how this exactly relates with Maxwell's equations. But I think just so happens the electron can form a nice standing wave in this region. And in this case, there is harmony. It's not emitting EM waves. Okay, it's not emitting EM waves. If a different mode of oscillation would have been set up, it would emit EM waves and probably pick one of these orbits and remain in one of these orbits. Complex stuff, but somehow trying to give you some way of understanding what's going on. Maybe once you guys learn quantum mechanics and embrace the wave nature of an electron more, maybe this will make more sense. But is there any other lingering down? Let me just check the chat. Um, anything anyone wants to add? Yeah. Yeah. So one of you is saying quite nicely. Actually, the theory of scientists are imaginative places. They live by imagination, nothing more, and hence we get such a variety of theories. Yeah, I mean that's true. I mean, to be fair, a lot of theories that, in fact, originally most of the theories that came up were purely imagination because they didn't have access to a lot of technology at the time. So therefore, there's a lot of different atomic models that were there initially, and we can't really discredit them because those models, we can't discredit their hard work because they came at a time where they didn't have that much insight. But I think now with the quantum mechanics is more or less, I mean, people are still working in it, but now that's more or less not just imagination. There are um, it's now a legit science. One of you saying ki, if there were different people at those times, the science now could have been different. Do you mean in a good way or a bad way? Because I don't think the people at that time have done too bad, given that they didn't have that kind of insight. Right? Even Einstein had a lot of work done before him that he could further build on. De Broglie, all these guys had work done before them that they could further build on. For them, certain bigger questions were answered by guys like Newton. So then they could focus on certain other questions. Is quantum mechanics a branch of science which could be studied in IIT? See, if you IIT has a lot of freedom. Quantum mechanics, as such, you're introduced to quantum mechanics briefly in briefly in chemistry itself. So in IIT, you're going to have a course called as chemistry in the first year. Everyone has it, whether you take chemistry or not. And in that, you'll be introduced to quantum mechanics. But beyond that, if you want to go deeper into quantum mechanics, you always have the option of doing extra courses from the physics department of IIT. By the way, are there two Ayush Mishras? I'm just noticing this, or it's you from the same device. Yeah, indeed, very exciting topic. Oh, there are two different Ayush Mishras. Oh, okay. One of the disadvantages of teaching in an online medium. Okay, cool, cool. So I think one of the Ayushs is giving me a quote. If you, this is by Richard Feynman, if you think you've understood quantum mechanics, you haven't understood a bit. So, I mean, I think that's, especially if you're going to go down the track of physics, I think one of the worst things a physicist can do is get arrogant and think that he has the answer for everything. Right? I think there's still a lot to explore, and the more humble a physicist can be, the more open-minded he can be, and the sooner he can lay aside his presuppositions and get real answers. So, yeah, if you're going to go down the track, exploring physics further, be exciting, be welcome, but always be open to be humble and be open to be corrected, proved wrong. All right. So guys, bye-bye. I'm guessing the lecture was till 5, na? 5:15 एक दूसरा lecture है तुम्हारा. Okay. चलो. Oh, yeah, guys, if no, I think a lot of people have left yet, but I hope they're going to hear the recording. So those who are here, just एक बार ये I want you guys to try this at home. I'll post this in the group as well. तो यहाँ पे just ये जो page है, since you've already done Bohr's once, just try this at home. We'll discuss this. Bohr में basically ये दो fundamental equation है. One is the obvious mechanics वाला equation कि centrifugal force is electrostatic force के बराबर, ठीक है, kz e square by r square is mv square by r. और दूसरा है angular momentum is nh by 2 pi. And with these two, in a way, like axioms, you can prove everything else, or you can find a formula for everything else. Now, mainly the formula for the first five are quite important, and I'll talk about that in detail. But I just want you to spend some time at home trying to get a formula for all of these. Okay, let that be like a practice question. This is like one of the main things in Bohr's atomic model. Can you use these two fundamental equations to derive results for the others? Okay, so just try that at home. R is radius. V, you're given what? You're given Z and N. You're given the atomic number and the orbit number. Okay, and you can use every other constant like capital K, small e, mass of an electron, h by 2 pi. You can use all these other constants and you can use Z and N. Okay, R का formula निकालो, V का formula, kinetic energy, potential energy, total energy, angular velocity, time period of rotation, de Broglie wavelength, linear momentum. Then electron moving in a circular orbit can be visualized as a current moving in a circular loop. So current, I for current, and current in a circular loop, you guys probably know now. Uske karan, it produces a magnetic field at the center. Yes. So B is the magnetic field at the center of the circular orbit. So just ऐसा practice के लिए मतलब थोड़ा most of this are done in camp. So just practice एक बार तुम घर पे ही कर लो. So that'll save us the time of you guys attempting this in class, since you know most of it anyways. And I'll discuss this nicely in the next class. ठीक है? First 5 का results हमें याद करना है in a way. तो वो मैं बता देता हूँ. And you just check the results. But ये page 8 please attempt कर लो, and I'll post it on the group once for those who probably left before I mention this. Okay, chalo. Lecture is going to be in the modern physics folder, inside a folder called as Bohr's atomic model. उसके अंदर support के अंदर मिलेगा. चलो, bye bye.